Hi everyone, welcome to part 1 of our video lecture on section 10.4 on the divergence, integral, and p-series test for convergence. In our previous lesson, we determined whether a series converge or diverge in a few different ways. The first approach was looking at the sequence of partial sums, if we could obtain one. The second approach was to determine if the series was geometric, and then to see if the absolute value of the common ratio was less than or greater than or equal to 1. Lastly, the third approach was to determine if we were dealing with a telescoping series. Then we looked at whether those interior terms would cancel out or not, thus giving us an infinite sum. Now, in this video, we'll begin to take a look at other types of series that are not geometric, not telescoping, and see if there are other tests that can be used to determine their convergence. These tests are the divergence test, the integral test, and the p-series test. So let's begin with the divergence test. The divergence test is also sometimes called the nth term test for divergence, and it's fairly simple. It states the following: if the limit as n approaches infinity for a sub n is not equal to 0, or if the limit as n approaches infinity for a sub n does not exist, then the infinite series of a sub n diverges. However, we have to be careful here because if the limit as n approaches infinity for a sub n is equal to 0, then the test is inconclusive, and we will need to do something else. But lucky for us, we're going to be learning new techniques that could help us answer this conundrum. And I also want to emphasize here that this is a test for divergence, not a test for convergence. Alright, so let's take a look here at a couple of examples. So we have the infinite series for 2n squared plus 1 all over 3n squared minus 1. Alright, so will this series converge or diverge? Well, let's go ahead and use the divergence test to see if it's going to diverge. So all that we need to do here is to take the limit as n approaches infinity for our sequence here, which is 2n squared plus 1 all over 3n squared minus 1. Now for this one here, if we go ahead and let n get arbitrarily large, then we would be dealing with an infinity over an infinity, which means that we have an indeterminate form and we can use L'Hopital's rule. However, I'm just going to go ahead and take a quick shortcut here involving the n behavior. So we know here that our highest power for n is second degree on the numerator. It's also second degree on the denominator. So the limit here is simply going to be the ratio of the coefficients. So for this one here, we have our limit to be 2/3. And there we go. This one here is not equal to 0. So we know then that the series is diverging. There we go. Now, one thing that I will point out right now, guys, as we're learning more and more tests, once you determine whether a series is diverging or converging, I want you to tell me how do you know that it's diverging or converging. Tell me which test you're using. So for this example, say that this series diverges by the divergence test. Alright, so taking a look at another example, we have the infinite series as n goes from 1 to infinity for e to the n squared. Now, applying the nth term divergence test, we're going to have the limit as n approaches infinity for e to the n squared. Now this one here is infinity, so the limit does not exist. Therefore, we know that the infinite series diverges by the divergence test. So not too bad. Now let's take a look at one more example here. So let's say that we have the infinite series here as n goes from 1 to infinity for 1 over 5n squared plus 3. Alrighty, so once more, applying the divergence test. So we're going to have here the limit as n approaches infinity for 1 over 5n squared plus 3. Now, if we evaluate the limit, we know that the denominator is getting arbitrarily large. Therefore, our limit here is equal to 0. Uh-oh, we got a problem here because remember, for the divergence test, if our limit was equal to 0, then the test is inconclusive. So, there we go. Now, not much we can do at this point. There's going to be more techniques that we can learn. Actually, we can go back to this one. Or, I don't know, I may put this one here on a future discussion board and ask you to find out, hey, is this series converging or diverging? With the divergence test, we don't know yet. But we will be learning more techniques that will allow us to know. Alrighty. So now, well, actually, one of such techniques that might work is the integral test. The integral test works in the following way. Suppose that f is a continuous, positive, and decreasing function on the interval from 1 to infinity. if f of n is the same thing as a sub n for all n values greater than or equal to 1, then the infinite series as n goes from 1 to infinity for a sub n and the improper integral from 1 to infinity for f of x dx either both converge or both diverge. So in other words, the infinite sum and the corresponding infinite integral behave the same way. Now, I do want to make something clear here. Although the value of the improper integral yields the value for the area underneath the curve, that value is not equal to the value of the series. Remember, when we were calculating the area underneath the curve, we were doing so by adding the area of an infinite amount of rectangles, which was the delta x times the height of the function. That was our integral here. But that's not the same thing as the sum as n goes from 1 to infinity for a sub n. So it's a different thing. Alrighty. Now, before we take a look at a couple of examples, I do want to mention the benefit of this test. If we can integrate the function, then we would be able to tell whether the infinite series will converge or diverge. So it's good. However, well, what if it's something that we can odd integrate? So what do we do then? The other thing that it's a little bit of a drawback as well is that we're limited to dealing with functions that are continuous, positive, and more importantly, decreasing. If you're not dealing with a decreasing function, then the integral test cannot be applied. Alright, so with that said, let's take a look at a couple of examples here. Alright, so the first series that I want to apply the integral test is a special series. It's a harmonic series, and it has the form 1 over n. Now, we are going to be encountering this series a little bit, or somewhat frequently throughout this chapter, so it's good to see it now. It has a special name, 1 over n is a harmonic series. Alrighty, so let's see if we can apply the integral test. So the first thing to do is to convert the sequence into a function. So I'll write here 1 over n as f of x equals to 1 over x, and remember, we want to see if this function is continuous, positive, and decreasing. Now for this one here, we know that we have to start at 1, and remember we're defining the integral from 1 to infinity. So this one here, if we're only focusing on values of x that are greater than or equal to 1, then yes, this one here is continuous. Now if you know how the graph looks like, it looks something like this. It's also positive, but we want to know if it's decreasing. So how do we know if this one is decreasing? Remember, we can always take the derivative and figure out, okay, well, what is the sign of the derivative? So taking the derivative for this one, we're going to get a negative 1 over x squared, and we're focusing on values of x greater than or equal to 1. And this one here is decreasing on the interval from 1 all the way to infinity. Alright, so it's continuous, positive, and decreasing, so we can go ahead and use the integral test. Alright, so using the integral test, we're going to get the integral from 1 to infinity for 1 over x dx. Now, since this is an improper integral, we do need to go ahead and rewrite it with limit notation, which is going to give us the limit as b approaches infinity for the integral from 1 to b for 1 over x dx. Now, evaluating the integral, we're going to get here the limit as b approaches infinity for the ln of x, and we're going to be evaluating this one here at 1 and b, which is going to give us here the limit as b approaches infinity for the ln of b minus, the ln of 1, which we happen to know that this one is 0. But now we have the ln of b, and since b is going all the way to infinity, then we have the ln of infinity, which is infinity. Now, if we were encountering this problem in the previous chapter, chapter 8, we would have seen that this integral diverges. So if this integral diverges, then the infinite series of 1 over n, this one here diverges. And how do we know that it's diverging? And again, you guys need to tell me how. This one here is diverging by the integral test. Okay, perfect. Now, let's take a look at another example. This one here was diverging, but what about the infinite series for 1 over n squared? Is this one diverging? Well, let's see. Can we use the integral test? Alright, so rewriting this one here as a function, we have f of x is equals to 1 over x squared for x greater than or equal to 1. And this one here again is continuous, it is positive, and is it decreasing? Well, let's see. Let's go ahead and take its first derivative. So we have a negative 2 over x cubed. Now this one here, notice that if the x values are greater than or equal to 1, then yes, this function will be decreasing. Okay, perfect. So we can go ahead and use the integral test. So let's go ahead and set up our integral. The integral from 1 to infinity for 1 over x squared to the x is going to be equals to the limit as b approaches infinity for the integral from 1 to b of 1 over x squared. And this one here is not too bad. We're going to get the limit as b approaches infinity for 1 over x. And validating this one here at 1 and b, we are going to be getting the limit as b approaches infinity for negative 1 over b minus a negative 1. Now this one here is going to go to 0. And we're going to be left with a 1. Perfect. So this means here that our integral is converging. Therefore, the infinite series will also converge by the integral test. All right, perfect. Not too bad, not too bad. All right, so what about an example like this, though? Now, this series here, as you can tell, it's very different from the ones that we just tried. So, can we use the integral test? Well, let's go ahead and take a look. On second thought, guys, I think I'll leave this one here for you to ponder, at least for a little while, because we're going to be going over this one in part 2 for this video lecture. See you there.